Welcome to the 8th episode in a series where I'm giving some tips and tricks on how to program using Arduino. So this is something new in this episode. We're going to be using a Rotary encoder to work with the menu that we had designed in episode 7. So effectively we're going to be building on top of what we already learned there. But before we actually get on to doing that, we'll be actually building a class to work with this Rotary encoder. So let's talk a little bit about the Rotary encoder first. This Rotary encoder is based upon an AS5600 chip. It was actually brought to my attention by one of my viewers. I had actually seen it being used in somebody else's sort of rotary encoded, very intelligent control knob. So I was sort of aware of it, but I didn't know the chip number or what it was. So he brought it to my attention. He was using it for a weather station, I believe a wind direction sensor. And what this is basically a chip with a complicated hall sensor arrangement built inside it that allows you to place a special magnet on top to find the specific angle. And that's pretty much all I knew about it. And I did order one, and it sat probably for a year or so in my storage box. So finally I decided to whip it out, and I thought it'd be a good topic for this episode. As a part of that, I built this little plastic knob here. It's basically just a turny thing. But I've also incorporated 2 buttons on it here. This is a design that I've come up with myself after very, very many 3D printing and experimentation. It's actually a little bit more difficult than you'd expect to make that. It has 2 buttons, an OK button on the right-hand side and a back button on the left-hand side. And the way I've designed this is so that you can do your normal turn action, but you can also click in the middle, which presses both buttons and allows you to navigate on another axis. So it's, I think it's a pretty cool little idea. Anyway, I'm going to provide probably a separate episode just to show you how to build this, and I'm going to try and put it on Thingiverse or something like that. Now, I don't normally give out code because I'm here to teach code, and I don't think just dumping out the code and letting you copy and paste it is going to be useful in the teaching process. I'm sure some people might disagree, but you're on the wrong channel if you disagree, so that's just the way it is. But as far as this 3D printing stuff, I just haven't had anywhere to stick this stuff in the past. But I'm not here teaching Fusion 360. I'm not an expert on it. I'm getting pretty good at it, I think. I like to think so anyway. But in any case, as it's not what I'm trying to teach, I don't mind giving you the files for that. So hopefully we'll give you that files, and there will be a dedicated episode showing you how to put this together if you want to make your own. Now, you don't have to use the one I made. You can just design your own or get somebody else's or whatever. But obviously this 2-button arrangement I think is pretty unique. So if you want to do it exactly the way that I'm doing it, as opposed to having separate buttons on a panel somewhere, then obviously you're going to need something similar to this as well. Let's talk a little bit more about this A5600 board. I did do a little bit of research recently, and the reason is because when I was making this, there's actually a tiny little magnet that comes with these A5600 chips, and I only bought one of them because I wasn't feeling that confident I'd get around to it anytime soon. And they come with this very, very tiny, I think it's 2mm by 4mm magnet. So I'd managed to stick it all out on my table there and start working with it. And by the time I'd finished designing my little knob here, I'd managed to lose this little magnet. The reality is that these magnets are so tiny, they're likely to stick to anything, or they're going to get in your carpet pile, or they're going to disappear. So this is my warning to you. If you buy this, make sure you secure these magnets in a safe position while you're working. So in any case, I ended up losing the magnet. I had to wait a couple of weeks before I ordered and received a new set of these. And in the process, I was looking on AliExpress, and I noticed there's a new version of this with a smaller board as well. The pin-out arrangement is a little bit different too, which I'll discuss in a second. But I bought these for $5 for 4, so it's about $1.25 per unit. So they're pretty cheap, and the quality of the board is quite nice. Let's talk a little bit about the board itself. You can see there's lots of different pins on here, and a few things I'm just going to point out first is that this device here is designed to work with 3.3 volts or 5 volts. But as it comes standard, this particular board comes configured in the 3.3 volt mode. And if you want to use it in 5 volts, which I'm using here with the Arduino Uno, you have to remove this R1 resistor. So you just need to desolder it or shift it off and remove the link. So all this resistor here is a 0 ohm resistor or a wire link effectively, which just links to 3.3 and 5 volt pins on this chip. Once they're linked together, it's working in 3.3 volts. If you buy the newest, smaller board, you'll actually see it has 2 pins on it, one for 3.3 volts and one for 5 volts. In that case, if you're using 3.3 volts, you actually have to connect the 3.3 volts to both the 3.3 and the 5 volt rail. If you're only using the 5 volt rail, you only connect to the 5 volt rail and leave the 3 0.3 volt open, and that's effectively what we're getting with this R1 resistor here as well. Also on the board you'll see, I can't remember exactly, but I think it's probably this R3 and R2, which are the SDA and SCL pull-up resistors for the I2C bus. So if you've got a lot of devices on the I2C bus, you're going to want to consider removing those pull-up resistors. Otherwise, if you have too many pull-up resistors in your I2C bus, you're going to slowly degrade the quality of the signal. And especially if you're working at higher frequencies, you will start to have errors. So just keep that in mind. And what else is on here? Well, let's just quickly look through the pins. VCC, which is your voltage in this case I've said 5 volts, and remove the R1 resistor. You have the ground. You have this out signal here, which we're not going to use, but there is the ability to output an analog signal or a pulse width modulated signal, PWM signal, relative to the position, which is good for standalone operations, but not relevant for our discussions here today. There's this GPO, which is actually for the configuration of the device. I don't know why O seems like output, but it's actually an input control. And I suspect this R4 here is the pull-up for that. So we don't need to use that. You can just ignore that. So we're going to do it all in code. SCL LCA for your I2C bus. And here's the big one. There's this DIR pin here. And the DIR pin is what sets the direction of the rotation. So originally when I started testing this device, it didn't work at all, and I couldn't figure it out at all. And that's because I had just left this DIR pin floating because I assumed it was irrelevant. But it doesn't even have a pull-up resistor. This thing literally is floating and flickering between high and low. And I actually saw on some posts somebody else had the same problem because it's an obvious sort of a problem to have, and I don't know why they designed it this way. But anyway, you need to tie the DIR pin to a high side 5 volt rail, or your positive rail, or the low side, the 0 volt, or your ground rail. It could work either way, but for me, I want it going positive for the clockwise direction, or a positive direction in my mind. And to do that, you need to tie it to ground. So there's actually a standard class you can get in Platform.io. And if you just want to totally ignore this lesson and figure out how to use that, go and use that guy's class. It's quite okay. He has information on GitHub how to use it. That's not what I'm going to show you here in this lesson. I'm not going to show you how to use somebody else's class. I think that class is designed to really wrap up all of the features of this chip, whereas I'm not going to really use any of the features of the chip other than just getting the position of A. That's all I care about here. In any case, my point is in his class, he actually has the ability to use a GPO to control this DIR pin. So he connects one of the GPOs to the DIR, and then you can dynamically change the direction. Now, you don't need a class to do that. You could just do that outside of a class in any case. So personally, I think it's unnecessary to have that complication. If you want to rotate the value the other way, then subtract it from 4096 or whatever, and you're going to get a reverse direction anyway. So I don't really understand why this is necessary. Basically, this direction pin is more likely to be tied up with the standalone type operation where you're actually using the PWM or analog output here. The chip also has the ability to lock and burn in values, such as where the position of 0 is. And I think that's, again, unnecessary. We can save it in the flash memory of the Arduino or whatever the microcontroller is we're using if we want to. So again, there's no need to do any of that. All we need is the number of the position, and that's it. It's probably also important to note that if you do start burning values into this, apparently you can only update the values 3 times, and after that it's toast. You can't modify the settings inside the chip here as well. So this is probably another good reason not to mess around with that. And again, this is all about having that function so that the operation of this could work standalone. You have some hardware device tied directly to some other hardware device that doesn't need a microcontroller, for example. You set it up, you set the 0 point and whatever. So yeah. I also just wanted to quickly point out that the neodymium, saying that right, magnet that comes with it is a special one. I think I mentioned it earlier, but the north and south poles are split down the middle, and that makes sense because as you rotate it, it will be able to detect where the north and south poles are position-wise. If it was polarized like your normal neodymium magnet, you would have to stand it like that and rotate it, which would be a bit of a pain. Oh God, where'd that go? Yeah, and you can sort of see why these neodymium magnets get away from you. They're very, very magnetic and tiny. So I think that's it for the discussion on this board. As I said, if you use a smaller board, it's pretty much the same thing. Just the pinouts on the power are probably different. Otherwise, I think you could probably use it without any problem, just as I'm teaching in this lesson. The connections, as I've wired it up here, all looks like a big jumbling mess. That's because I've got it set up ready so that we can show you how to use it with the menu later on. So first we're going to make the class standalone for this module and test it standalone using the serial terminal, and then we're going to go on to using the menu that we made in that last episode. So I'm just using this intermediate breadboard here so that I can gang up the I2 squared bus so that the display and the A5600 will be on the same bus. It's interesting to note that the bulk of these A5600s have this A5600 chip, and there's another variation of this chip called the A5600L. Now the L version, I believe, is the one where you can actually change the address of the device on the I2C bus. Unfortunately for this widely distributed version, the address is fixed to hex 36 and you can't change it, so it's a bit of a disappointment really in that regard. There's no jumpers or anything on here that we can change the address. So for this lesson, that's what I'm going to be focusing on, is the widely distributed variant. If you're using one that can change the address, which I believe you have to change via programming it, if you do that, well, you'll have to figure that out separate of this lesson. So you'll notice here that I've got the display disconnected, and that's because I just noticed that when I had it all connected and just tested the class for the A5600, it wouldn't work. I'm not really sure why. It could be something to do with the fact that I'm having the doubling up of the pull-up resistors on the I2C bus, because obviously there's pull-up resistors here as well. It's not really entirely clear for me, but in any case, ganging them up together when I'm just testing the A5600 wasn't working, so for now I just disconnected it, and I'll connect that back up when we're getting it all working. So all I've got connected here is the two buttons, which are going to a port on the Arduino Uno, which are switching to ground. Then on the A5600, I have the power and the ground connected. I had the SDA and SCL connected to the Arduino Uno's SDA SCL connections, and I have the DIR connection connected to ground. Okay. All right, I think I've waffled enough on the intro. Hopefully we've lost about half of our audience by now, and that'll be excellent. Oh, and by the way, we just hit 3,000 subscribers. Only took 4 years. It's quite an amazing achievement. Anyway, let's get on with it. All right, so the first thing I've done here is I've already created an Arduino Uno test project in Platform.io. I'm just going to clean up some of the garbage here that comes with a new project. So in this project, we're going to be really testing the connectivity with the A5600. That's obviously one of the primary things we want to do, make sure we can connect and talk to it and get the values back out of it. To communicate to the A5600, we need to be able to use the wire class. So we're going to have to include that in here. The other thing we need to do is set up the serial port, because we're going to use the terminal for the testing. I'm not going to use a display or anything like that. We're just going to dump it out in the test terminal display here on the screen. Speed we're going to use, it's going to be 115200. I think I got that right. And as we're using a non-standard speed or a faster speed here, we also need to specify that in the Platform.io ini file as well. I'm just going to paste that in there like that, 115200. Okay, we're going to set up a constant for the address. 36 hex is the address we're at. And we're going to make a little subroutine or a function that will allow us to go and grab that position value that we need to get. And that's the only thing that we're going to be getting from this AS5600. We don't need to get anything else. So there are actually a range of values that can be interrogated on the datasheet. The two types of values that it can return is either an 8-bit or a single byte value, or a 16-bit or a 2-byte value. In the case of the position value, it ranges up to 4095 from 0. That's returned as a 16-bit value. So I'm just going to create one simple function that interrogates the A5600 for a 2-byte value, basically, or 16-bit values. We'll stick it up the top here so we don't have to double declare it. So read 2-byte register. I'm just going to write reg, so uint8, and we can tell it which register we want to use. Now, obviously, we're only getting one value, so we could have just hard-coded the register. So to be quite honest with you, I'm not really all that clear on the process of the wire transaction. The reason I'm not really focusing on this is because it doesn't really matter that much for what we're trying to do here. All we need to do is get this 2-byte value out of the device, and that's fine. And if we don't understand it in full detail, it doesn't really matter. This is not the objective of the lesson. The lesson is about using a value returned from this A5600 device and applying it in our project. So let's just sort of wade through this in a very rough fashion, because I'm not entirely confident about the nitty-gritty of the wire object itself. So anyway, as it was written, we need to begin the transmission at the address. Then we need to request the specific register that we're working on. We need to do a quick check to see if the, here we go, not equal to 0. If it returns something other than 0, then I'm assuming it's returning some sort of error code. But in this case, the transmission is not working correctly, so we're just going to return a value of 0. For this test, that's fine. So the next section, we are going to do the request for the 2 bytes. So uint8, the number of bytes, request from, we need to put the address, AS5600 address, and the number of bytes that we're requesting. And we need to specify this as a uint8 value. And 2 bytes is what we're requesting, which fits with our read 2 byte register scenario. And in the next section, we're going to look at this return value. And if it doesn't equal 2, well, then we didn't get 2 bytes back. It's a failed state. So if n is not equal to the 2 that we wanted, then again, we're just going to return 0. So as I continue to understand it in my very limited knowledge of this wire object, I understand at this stage the information has been read into the wire object's buffer, and we need to take it out of the buffer and return it as a part of this function in this case. So we're going to do that next. Just going to call it underbar data for now. So this is our result value, and we are going to use that wire object again and read the value out of the buffer. It could be coming out of the buffer, it could be reading it directly from the device. I really don't know about the internals of it, but I suspect it's coming from the buffer of the wire object. And what that's going to do, and what I am sure, is it's going to take the first part, the upper byte of the 2 byte pair, and it will load it into the lower part of the data value. We have 1 more byte to get, and we want to shift it into this uint16 value. So to do that, we actually need to shift this 8 byte value up into the higher position. So we can use one of the wonderful features of C. It's very rare that I'm sort of being nice about C. You can use a bit manipulating function, which looks like this. Shift the bits to the left. I'm going to shift it 8 bits, and that will take that value that we read here into that lower part of the 16-bit register. It will shift it up into the higher part. And once again, we have another function for adding the lower part of the value. We can plus equals the wire. Okay, and then we can return the data. Let me paste in all of my comments here. So with any luck, that's going to work. Let's set up a little routine so that we can actually read that data. In the setup, I will just add a little sort of init value so that we can tell that we're connected. So we're not actually doing anything yet. Let's see that it will build and run. Very basic stuff. Just want to make sure that the terminal is actually working here. Initialize, okay, so we know we've got basic functionality here. So in this loop down here below, every certain, say 250 milliseconds, it doesn't really matter. Let's actually set up a define for that up the top here. So, all right, for this test, every 250 milliseconds we'll do it. And I need some variable to track when we last updated. Alright, so these are the values controlling pacing of our getting information. So this loop is going to be looping here constantly, and to pace it, we'll just use something simple. So here, all we're going to do is see if we can get that value from this function here and write it to the screen constantly. Serial.change line, better way to go. We will read the 2 byte register, and we need to identify which register it is, and I've forgotten, so let me just check. We're going to set up another constant for that as well. Okay, so that's going to be the register address within the AS5600. So serial print line read 2 byte register, and AS5600 raw angle is the register that we want to read. And I got an error here. Let's run it. Okay, so twist the little knob here and see if the value changes. Oh, and it does. And you'll notice that the value is relatively stable here. It will only dance between maybe 1 value at most, which is pretty nice. And the range should be up to 4095. So let's keep winding it up. Yeah, you can see there. See if I can get it right on the edge here. That's 95, 94. Yeah, there you go. So it's dancing there between 4095 and 0, which is right on the margin of the changeover. When I reset it, we have this number that comes after the initialize OK, and that's because I'm not print lining on the initialize OK. Let's just send that. Tiny thing, but it annoys me, so let's just fix it. Yeah, so the serial port is hammering away there, so it wouldn't upload for us. So I found this before. You need to try and upload a couple of times to get it to work. And yeah, that's clean now. All right, so that's it. End of lesson. Nah, just joking. Wouldn't it be nice if it was that easy? But unfortunately, it's not. Let's make this class. It's going to follow on from what I already pretty much went over in that last episode. So I'm not going to reteach what I've already taught. If you didn't watch the last episode, watch the last episode before you try to do this. So I'm going to create a new folder in this library location. And it's going to be called AS5600 Notched. I'm calling it Notched as the name of the class because that's my objective, is to have the knob function with virtual notches. So obviously we need in here a couple of new files. The .h file and the code file .cpp. All right, let's start off with that definitions file. Yes, readme. We already followed that in the last episode. So as with the last episode, I'm really just going to go through and type out the definitions first. And, you know, I sort of always get a bit worried about if I'm twisting the process a little bit about how you might actually make your program. The reality is that what I'm showing you is pretty close to what I did in relation to developing this class. And so it is following that order of operation. All right, let's get into it. Obviously, we're going to need Arduino in here. Need to include that, and as we saw before, we needed to include the wire. And we have a few constants. We just take these two here, which we can reuse. And there are a few other special constants which I will add. The first is the default notch size. Now, when we're talking about notches, we're talking about as we turn the knob, certain number of steps, we want it to switch to the next position or the next notch, basically. Within that, every 64 positions, it will be my default notch size that I'm going to use. And then we're going to need a minimum and a maximum size for the notches. So as we saw, that the resolution is pretty accurate within 2 digits, basically. So you saw it flicking between 0 and 4095 or whatever the value it was. So there's a little bit of flicker sometimes. So we want to have the notch to be greater than 1. So in that case, I'm forcefully saying that the minimum notch size will be 2. And as the maximum range is 4096, maximum notch size I want to use is a division of 4 of that. So 4 slots, basically. I think that's as big as you want to go. So 1024. So there we have all of our constants. Now let's get to making the class. We'll define all of our public members first. And obviously in the last episode, I think I showed you we have private declarations, which are things internally used by the class. There's one other type of element to a class different from public and private, and it's protected. It's a little bit difficult to explain if you don't really understand the way classes work when they're used in inheritance mode. But one class can be derived from another class. So if I made another class, I could actually inherit all of the features of this class. And as a part of that, I may want to manipulate some of the internal components of this class. But any elements that are private can't be manipulated. To make a value manipulatable by an inheriting class, you need to make the values protected. So it's a pretty good habit, you know, if it's not too critical, and it rarely is critical, to make those things that you might feel like you want to make private in a class, to make them protected. The key thing is you could use private, but protected will make it more flexible for the future when you want to actually get to using more advanced features. So those are the two sections, and I'm not actually going to define any private elements to this class. So the initializer. So as a part of initializing the class, I want to give the ability to hand over an alternate wire object. Now, obviously, the default wire will be there, and I could just use that. But as in this case, for example, the AS5600 has a fixed address, it might be the case where you want to have multiple devices connected, and your microcontroller might have more than one wire device. So it's just a good policy in a way to make it configurable. So at initialization, we want to be able to enable the ability to hand over a reference to a wire object as opposed to a value as such. So references are handed over a little bit differently. So the way that we have to do it here is toWire is the object type, and we want to hand it over as a reference, so star wire. So if I just write it like this, then every time we initialize, we would actually have to hand over that wire object that we used earlier on when we were testing the connection. But what we can actually do is we can set a default value in these definitions. So this is something new that you haven't seen before. But when you're predefining a function, be it in your normal main CPP code or in a class definitions, you can actually hand over a default. And in this case, what we'll do is we'll hand over the reference to the wire object itself. So what this means is that we can now initialize the object without actually having to define the wire object. It opens up the window to allow you to define the wire option if you want to, but you don't have to specify it. Next up is we have the actual value, a value from a range that you are working with. So not the raw value, but the value that you want to manipulate via this knob. So here we go. So I'm using an int32 just to have a fairly huge range, and it also allows negative values as well. And we're just going to call it value. And also we want to define the maximum minimum range of the value. So the way this is set up here as public members of the class, they're just raw variables. They're not functions or anything like that. So you can manipulate them at any time, and I think that's fine. There are two other of these publicly defined variables that I'm going to use, and they're enable or disable function flags. So let's think about how this thing's actually going to work. Every time we move the knob by the degree of the defined notch size, it's going to modify the value up or down. And then we have these mix and max value ranges. And so what this range limit enabled will allow us to do is to say, apply the range limit. So if we hit the minimum value, it's just going to find the end of the range there. It will stop. And depending on whether rollover is enabled or not, for example, if we're going from 0 and we're rolling up and the maximum is 10 and we hit 10 and the rollover was enabled, then it would roll around to 0. But if the rollover was disabled but the range limits were enabled, then it would just keep going up until 10 and then stop at 10. So that's the basic sort of functionality that we want. And that makes a lot of sense. If you're thinking about a menu which has 5 items, you might want to roll down between items 1, 2, 3, 4, 5 and then stop, or roll back up with knobs. So that's going to be quite a useful sort of functionality to have. So next up, we're going to start working on the functions for the class. And the first thing we're going to do is set up an initialize function. Now this initialize function will just go out and get the current position value and lock everything together with relation to your current value, for example. And I'm returning the status of the function as a Boolean. I guess that if the initialization fails, it will return false. Now, something new about building a class, which I haven't discussed, just like I hadn't discussed the ability to add defaults to definitions, there is something you can do when you're defining functions in a class. And I believe the same thing goes for function definitions in your main code here. I don't think there's any differentiation between the two. You can actually do something which is called, I'm not sure if it's the correct terminology in C, but something that I understand the name as being called overloads. And overloads means you can have multiple versions of the same named function, but that accept a different set of variables. And as long as the set of variables are unique pattern, you can have as many same named functions as you like, accepting different criteria or different variable inputs. For example, the initialization here doesn't accept any variables, but you might want to set it up so when you initialize, you provide the value and you provide the units per notch. And there is going to be one more version of this initialization, which I would call the almighty initializer, and that's going to have the maximum number of criteria available. And I'm also going to add it with a bunch of defaults as well. Until here we can do the same. Then I also want to provide the min and max. Start on with some of the optional items. With the optional items, once you have a optional item, every other item afterwards also has to be an optional one. And if the user provides a value, say for example, he wants to provide a value for the second optional value in the lineup, he must also provide a value for the first one as well. That's sort of the way it works. So the order of these does matter. And I try to order them in the likelihood that I would want to set this value, because if I set a certain value, then every value before that was optional, I also need to configure, which gets quite cumbersome if you have a lot of those as well. Anyway, let's do these optional values. So first one I want to do is this rollover enabled. Now you'll notice here, I haven't added an option for range limit enabled, because the logic goes is that if you're specifying the min and the max, you're going to want the range limits enabled. So it will automatically enable the range limits because you're specifying the range limits. And next up, we want to have the notch size. And again, we're going to use a default. And next up, I want to have an ability to use an exponential type movement. And what that means is that if you spin the knob faster, the faster you move it, the faster it will adjust the value. It's just an 8-bit value. And I think the value will be between 0 and 10 is the option. 0 is disabled and 1 through 10 is the degree of which the exponential will be applied. EXP for exponential. I'm not sure if there's a great name for it, but that's what I decided to call it. Again, separate to that, we have one more special feature which I added, which was the ability to lock the value to a specific physical position on the knob. So for this locking of values to work, there are a couple of rules that I apply. Fundamentally, it has to work within a single rotation, and the notches have to be an equal division of that 4096 dial space. Anyway, let me add that. I'm defining it by default at 4096. So if it's outside that valid range, it will disable. So this is basically by default disabling it. So those are the three initializers that we have. Thankfully, the following functions are not that complicated. So this is the primary function that's doing the heavy lifting or doing the work. This will actually get the value from the AS5600 and update your value in relation to whatever the current value is. To realign to current roll pause. So it's basically just aligning your current value to be matching that of the current roll position from the knob. So that's really recentering you on the notch is probably a way to think of that. So this is just a function to figure out if your last read was successful, so you can actually confirm the connectivity with the device. Last roll position is just going to provide you the last value that was gotten from the AS5600 or the roll position. Get roll count per notch is just allowing you to have external accessibility to understand what the current roll count per notch was. I mean, you're setting the value, so you should already know, but it will provide accessibility. But I am providing the ability for you to set it. But again, because it's a managed value, it has to be set in a very certain way. So this is going to return a Boolean value as to confirm that it was able to actually set that roll count that you wanted to set or not. So again, access to another internally managed variable, the exponent level. So that's pretty much it for all of the public stuff that we want to present. Anyway, let's keep going. All right, so next up are the protected ones. And these protected ones will be differentiated by using this underbar at the start of each of the labels. I think I don't need to explain that. Or that. Or that. So that's the last red raw position. That's where the value will actually be saved from the raw value that was red. And so this is a little bit more less obvious stuff. This is related to the exponent, and I don't think I want to discuss it too much here, but there are two values that I'm using to track the speed of movement. So this is actually a little bit of an interesting variable. This one here is what's actually tracking which notch position we're in, but it's tracking it as a raw value. So when you actually go and move to the point where the notch changes, it's going to save that value in here, so we can actually track how far we're moving in relation to a notch based scenario. And now we also need to have the 2-wire object. And this is a reference style object, so we have to have a little star there, and we're going to call it underbar wire. I'm going to have two private functions. It doesn't need to return anything. One to set defaults, and we're going to also have that function that reads those 2 bytes from the AS5600. Okay, still not sure why I'm getting this error here. Oh, I know why. This is missing here. Boop. You see? Need a semicolon over here. Need semicolons everywhere because it's C. Alright, so the protecteds are all set up there. And once again, I'm just going to copy and paste in all of my comments. The layout's a little bit different, it's the same content. So let's get on to writing the class code. When we're dealing with the class, we need to connect to that .h file. And in here is where we're going to add all of the functions that we need to add. So all of the functions, why don't we just copy and paste all this for a second. The first thing we've got to get rid of is things that are not functions. So these variables all got to go. All of these variables have got to go. And what we're left with is a bunch of functions. This is also the function, but this is an initializer. Before we get to that, why don't we move all of these and add a little squiggly bracket here. We're pretty much done there. I'm just going to move the indents out. We don't need any indents. And the other thing that's missing is we haven't linked in all of these functions back to this class yet. We better do that too. And so to do that, we have to, I'll just copy that, AS5600, : All right. So we need to add this AS5600 notch, : to link these functions. In this case, this is the initialization function, back to the class as we defined it. So we better go and do that on every one of these functions. Okay. Huh? What's this one here? Didn't think I was reading. Oh, this has still got the stupid colon here. Oh, okay. That's good. And if we try to build it, what does it do? So I was a little bit surprised to not see an error because I didn't think you could do what we're doing here. As you can see, all of these default values have been left in place, just like they are here. And so we're defining the default values obviously here and here. I thought that wouldn't work. Yeah, it shouldn't be necessary. So having the defaults in two locations means it's more complex to manage. Yeah, I don't know, it's a bit weird. Let's get rid of the default here. Still build fine, I'm sure. I mean, for example, if I put a different default in here, will it build? It will. So now we have a default here in the functional code as well as in the definition, but the defaults are different. So that's quite confusing. I think we'd want to avoid that sort of risk. So I'm going to get rid of these doubled up definitions of the defaults just to keep it tidy. I guess it would be fine to leave it there. I suspect one or the other would be overridden and unused, but that's confusing. So we just have the defaults which are defined here, and in the actual code I'm removing the defaults. It's a bit confusing for me. The fact that we have to double define everything anyways, as you probably can tell from every episode where I complain about it, is totally insane in any case, but we're only using it in these two functions, if I remember correctly, where we're using defaults. So for now, the default values are only set in the definition of the function, and the actual code, I'm just removing it, so that's fine. All right, so let's get into the nitty gritty. We can start with the initialization, which is going to be pretty straightforward. First thing we want to do is that we're going to take this wire object reference that we're being provided, which would normally be the default wire object, and we're going to save that. And the other thing we're going to do is call the setDefaults function, which is an internal function. Add the comments, and why don't we just go straight to this setDefaults. Oh, that's the wrong way to do it. Always get confused between definition and declaration. So setDefaults are here. Set the value to be equal to 0. The min value to be equal to int 32 min value. And I'm going to shift it up. And the max value, same thing, but on the max side, minus 4096. The range limits enabled. No. The rollover enabled. No. Exponent level disabled. And the raw count per notch at default. Alrighty, nice and clean. Here it is with the comments. For the exponent level, 0 disabled, 1 weak, through to 10 for strong. All the rest is pretty straightforward. Let's keep going. what are we going to do next? Why don't we try to get this initialized value, the basic one, working? So, first thing we want to do is set up the defaults. Even though we did already set up the defaults when creating the object, we can also set up the defaults again just to make sure we're in a known state when we initialize. And now we can grab a copy of the last raw position. Read those 2 bytes. Just going to raw angle value like we did before. And we'll also just capture the time in microseconds. So this read 2 byte reg function hasn't been fulfilled yet, so we better go do that. Fundamentally, it's just going to be what we wrote earlier. So why don't we just copy and paste that and modify it so the errors go away. I'm going to be careful what we're doing here. So we don't want to use this wire object, the default one. We want to use the one that we have created the reference to. So we better replace that. And this dot is no good. So when we're using a reference type connection to an object in C, we need to use that stupid arrow nomenclature. We can't use dot, whatever. So we better replace it up to the dot. And the object that we're using, the reference type object, is called wire, right? With the underbar wire. And we're going to use this minus greater than sign. And how many have we got? We've got 1, 2, 3, 4, 5, 6 of those that we need to replace. 1, 2, 3, 4, 5, 6. Okay. We have this variable here called last data read OK. And so when we don't read OK, such as when we're returning 0 here, we need to set the last data read OK equals false. That's spelt wrong because it should be underbar. So we should be adding that to each of these failed cases, and if we succeed, we can set that to true. Okay, so it's fundamentally the same, but we're using the reference-based wire object, and we're manipulating this last data read OK value to track if the read was successful or not. And there it is. Cooking now, cooking with gas. So set defaults. We read the value. What are we going to do next? It's all so exciting, isn't it? So let me just add the comments on this top section here that we've sorted out, just like that. Now there's actually meant to be a little bit of stuff in here which we'll add a little bit later for some of the exponent initialization stuff. But I don't want to talk about it now because it'll just be confusing. Alright, so we'll skip that for the minute. But one of the things we can do is we can fail out if this initialization doesn't work. So if we couldn't last data read OK, which we just set in that read 2 byte reg value, then we just can go ahead and skip out here and return false. But assuming we did read it okay, we can save that last raw position into the selected notch raw position, so we can lock the current value with the current physical position, in effect slotting it into the current notch. And if we get this far, we're doing pretty good. So let's turn back a happy and positive. Add the comments for that. And we can go on and do a few more of these initializations. This one's quite complicated up here, but this next one's pretty simple. So the first thing we can do is the basic initializations, and we can check the status of the basic initialization as we go. So if we'll initialize there and it's no good, then we can return false. That makes sense. And in this case, we want to set the value as well. It's not complicated. We just go value equals the value that we provided. Then we want to set that raw count per notch. Now that's actually a function that we have to create, and it has some rules and limitations. So we'll do that in a second, but we'll just call it for now. Set raw count per notch with the per notch count that provided. And if we get this far, set that true. Let me just copy the comments there, and we're going to go to this set raw count per notch. So all this routine is really doing is just providing a safety net to make sure that the value that is trying to be set is within the valid range of allowed notch sizes. So as long as the notch is within that valid range, I just noticed that I'm using a different label here that I used in my original code, so I'm just going to change that. But I actually called it per notch. Alright, if the provided per notch greater than or equal to minimum notch size and provided per notch is less than or equal to maximum notch size, then we're all good, right? We can return true. Otherwise, we don't actually need an else, but I'm just going to write it as an else. We can return false. Couldn't do it. Bad value range. Believe it or not, I didn't even bother writing a comment for that. Okay, so now we have the two initialization functions complete. I'm a little bit nervous if we want to go on to that third one. Maybe we'll do it, and you'll just have to like bear with me on it. The first thing we're going to do is basically call this routine, which we'll in turn call this routine. So, and that will set up the value and the per notch. So there's a safety net there. If it couldn't initialize, it will return false. And now we can use these other values that are provided. So the min value equals the min, the max value equals the max, and range limits enabled is true because we're using range limits. And next up, we want to set the exponential level, which I think I'll skip at this stage. So set exponential level, which is the function that we defined earlier, but we haven't written yet, with the exp level provided. The rollover state. There's another tricky function, which again we might do a little bit later. Set value to raw relation, min rel was. And finally, we get this far, we can turn true. Okay, so I'm going to do these two later because I think it's too confusing to do it now. Otherwise, everything else makes sense, right? So there's the comments. I'm going to add my do laters back in. Do this later, okay? Anyway, let's have a quick look. Got our initialize stuff done, which is most important. And how about we just do a couple of these little things first. This set value to raw relationship is probably a little bit complex. We can do that a little bit later. It's realigned to current raw pos. Yeah, probably easy stuff. So these bottom three here are simply just returning a value, I believe. So this first one, we just need to return that protected variable. Last date read OK. Provide external accessibility to that. And this is much the same. Last raw position. So that just provides us the access to that raw position. And this is, again, this is a setting, an internal value, something that can only be set using this function down here below with the limiting range. But we can also access that value here. So let's do that as well. This exponent level stuff, I think we'll do that when we do the exponent altogether. Might be a better way to do it. No, let's do it now. It's not really all that important in relation to the functionality, and we're just basically returning and setting those values. So let's just do it. The set exponent level, this is similar to this set raw count per notch. There is a limited range which is acceptable. So what I might do is just copy this. And the range here is 0 is the minimum, 10 is the maximum that I'm allowed. So basically you can set 0 for off and then 1 through 10 for the degree of the exponential adjustment. And obviously this per notch, it is not, it's level that it's coming in as, so we'll modify that. And the value we're modifying is, somehow I've got this wrong here as well. The exponent level, okay, that's better. So we'll return it there as exponent level, and we will set the level and return true. Okay, so that's it. So we have all of these little sort of accessibility and setting capabilities all done. The other one here, realign to current raw pos. Well, this is actually pretty similar to the initialize state. When you initialize the class, it will always go ahead and get the value and then lock it here like this with the into the notch, the last raw position associated to the current value. So we don't actually change the value, we actually change the reference to the position on the dial that relates to that value. So it, as I said, it looks pretty much the same. So we can just take this, probably could just repeat this code as a separate function, but we'll just do it this way here anyway. We don't need any of this exponential stuff here. And assuming we get this far, we're going to just do the same thing, right? Like that. Okay, so I think I've explained that fairly poorly, but the point is it's basically the same as a cut down version of the initialize. All it does is it goes out and gets the raw position again, and assuming that was successful, it relocks the current selected value to that raw position, so it's centered to the notch. I think we've done just about everything, which is, as I said, not a real representation of the order that I might have written this originally, but it's not too far from reality either. So now we're going to get down to the update value. So this is the routine that we will call every so often to get the value from the knob and adjust our actual value relative to the amount of movement on that knob. So there's a couple of rules here we need to understand when we're actually doing this update value routine. First thing is we need to do it at a certain frequency. And I'd say the minimum frequency that you want to do it is it's not a frequency, but a minimum time frame you want to do it is, say, for example, every 25 milliseconds. And the reason for that is that the positions that we get from the AS5600 is just related to the current rotation position. So it doesn't know how many times you've turned it. If you turned it 10 times in that 25 milliseconds, well, then it wouldn't know that you turned it 10. It would just know the position. So the idea of the high frequency or the regular updating of the value should mean that we are capturing the value fast enough that the user wouldn't be able to turn the knob beyond a full rotation. And as we'll see in a second, it's actually beyond half a rotation because we only have a full rotation to deal with, but it could be a negative rotation, in other words, going anti-clockwise, or it could be a forward rotation. But obviously, when we meet in the middle, we've only got a half rotation in either direction. So the reality is that we need to set a frequency which is fast enough that the user wouldn't be able to turn a half a rotation within that time frame. Less than 25 milliseconds is doable. If you're getting up into the 100 milliseconds time frame, you might be able to spin up a very good moving wheel to get it faster than a half a rotation per 100 milliseconds. So yeah, 25 milliseconds is what I'm generally targeting, but there's no time frame set in this class. It's up to the external code to manage that time frame. In your code, you will have to manage that frequency. The frequency doesn't need to be exact, but it should be generally a regular pace. So the first thing we're going to do when we get in here is replicate this bit of code here, which you see now the third time that we're using, and that is just going to go out and update that raw position. And before we actually go into anything else, how about we get the code working in our main CPP so it now works with this class, and then we can progressively increase the functionality of this update value routine and confirm at each step that it's working, which is something that I recommend you do. So we can get over here. We don't need pretty much any of this stuff anymore. This frequency of update, which is currently 250 milliseconds, let's just leave it like that for the minute. So instead of using this print line read 2 byte from this function that we created before, we're going to get rid of this function and we're going to depend on our class to do all of the work. We don't need any of this. Let's comment it out. We don't need a reference to the wire anymore because that's all handled by our new class. But what we do need to do is include custom class that we made. So let's do that. I wonder if we can get it like that. Yeah, there it is. So now we have our custom class. We also need to create an instance of the class object. Custom class AS5600 notched. And I don't know, I'll just call it knob. Sounds like a terrible name, but knob. It's not kebab. Oh dear. So here we have our object. Now we could hand over the wire object if we wanted to, but in this case we're just going to use the default wire and type it like that, and it will initialize with the default wire. So when we define it like that, the first thing it's going to do is run that constructor code, connect up the wire internally to that wire that we want to use, and set the default value. So it's not actually reading any of the values at this stage. So we still need to initialize the knob, and we're just going to use the basic initialize, no values, keep it nice and simple. Why don't we also just add a little bit of code to make sure that it's working correctly as well. So if the knob initialized, in other words, connected to the knob, then we can print this. Otherwise we'll print initialization failed. And over here, instead of printing line of that function, which we've now commented out, we're going to get it from the knob. Last raw position, that'll be the one. And that's a function, right? Yeah, there we go. So that's only going to read the last raw position, but we're not updating the raw position. Let's do it this way. If knob update value works, then we're going to print that line. Otherwise, if we stop getting updates, we just stop printing to the screen. So if the knob value update's okay, we're going to go ahead and print the screen. Otherwise, we're going to do nothing, and it's just going to rotate around here every 250 milliseconds, which is fine for this just initial test because there's no control logic in here. We're just getting the value. Oh, we better send back all okay as well. And that's it. Okay, so really very overcomplicated way just to get the raw value. We're just going to read that raw position, put it into the last raw position. We'll check if the last read was okay, and if it wasn't, we'll return false. And if we keep going on, obviously it was okay, and we'll return back true. Will it build? What am I forgetting here? It's complaining about the lack of the return statement here, but this is not an issue for now. It's just a whinge, so we'll ignore that. So let's upload it and see if this works. I need to manually switch back to the serial monitor. Okay, so it initialized okay, and it looks like it's reading a value. Let's see if we turn the knob. Yeah, so it's basically doing what we saw before. Let me disconnect the I2C bus and see what happens. Disconnect it, it stops updating, and if I reconnect it, it continues to update. And if I disconnect it, and I reboot it with the reset button here, you would have expected it to time out and give you an initialization failed. Let me reset the terminal. Well, that's not operating as I expected it would have. And if I reconnect it, let's just see. In theory, it should be getting stuck even before here, right? So let's add one more little test line here. So if we get through this far, we'll get that serial okay. Serial okay. But if I disconnect it and I reset it, oh yeah, it does a serial okay. I find that surprising. It doesn't look like the behavior that I prefer. So it's clearly getting hung up when it's trying to read. I wonder if there's some sort of timeout on this wire object. And we can set the timeout up here when we initialize it. Oh, we got the initialization failed. Seemed a bit faster than 2 seconds. Let's reset it and just watch it one more time. Weird, right? It seems like it doesn't wait at all. And if I connect it, but I reset it, oh yeah, it's working, right? But there's no way that timeout is happening in 2 seconds, right? Maybe we can like really ramp it up, give it 20 seconds, and let's disconnect that. Initialization failed. I don't think it waited 20 seconds. What is going on? I really have no idea. I think I'm just going to leave it to the default. Seems you don't need to even specify a value because this set wire timeout defaults to 2500 U, which I guess is unsigned integer. And I guess that's going to be good enough for what we're going to do, and it saves me having to configure it. So alright, I'm not really setting, I'm just going to enable the timeout on the wire so it doesn't get hung up like we saw before. Just one more compile and test to make sure it all looks good. Still disconnected, so reset, reset, plug it back in, let's get back on with what we're doing. Okay, so for this next section, we're really going to get into the nitty-gritty of things and really focus on the core thing we're trying to achieve here, which is to manipulate the value. Actually, I had to walk away a little bit and revisit this in my mind so I could try and explain it in a somewhat sensible way. I nearly just thought I was just going to write the code and tell you to type it in, but I think it's not useful just to type in the code and not understand what you're typing. So I'm going to make an effort at explaining of how this works. I also, when I was thinking about and revisiting how to show you this, I noticed I had a little bit of a bug in the code that we already wrote. The bug was such that it's actually self-rectifying, so it doesn't actually cause any negative issues. But we're going to fix it up as well just to make sure that it gets rid of the confusion, which was confusing me when I was trying to review and revisit the code as well. So anyway, the key point is that the last raw position we get is between 0 and 4095. What I am doing is I'm shifting that value up by one whole unit block or one whole rotation, or 4096, and that just makes it a little bit easier to work with. And I'll tell you why later on. But for now, the first thing I want to do is I want to create a working value in here which has that offset applied. So the idea is that even though I am tracking the original raw value, all the workings that happen inside here is meant to happen with the offset applied. And where I made the miscoding is when I'm initializing, for example, this selected raw notch position, I haven't applied the offset. I forgot to apply it. And as I said, it self-rectifies itself in its code, so it never actually appears as a bug. But it is confusing because these values are meant to be in the same number range, but they are clearly not in the way that I've written it. So what I'll do is fix wherever I'm declaring it. And I think we're doing it a few different places here, if I remember correctly. Anyway, I'll just replace them all. I'm just going to copy this whole section here, Control F, and I'll add the 4096. And it says there are two cases where I'm doing that initialization. So let's fix that. That's 1, 2. Okay, so now we've added the 4096 offset also to the selected notch raw pos value as well. And maybe I'll fix the comment here as well. Okay, so now we have removed the confusing part. All right, we're back into the update value and we've got our working value. So what we need to do is we need to figure out how far we've moved from our current last selected notch position, which relates to our value, and the new working raw value that we've got. And obviously once we know the distance, we can recalculate that based upon the size of our notch setting and figure out how many units we've moved and apply that to the final value. But for now, we just need to know the distance in total raw space, negative or positive, that we've moved. And this is where the explanation that I've come up with will come in. So let's try and do it. I'm just going to copy and paste as we go because I've already prepared a little bit of discussion work here. The first thing is that we have this number range, and I've just written it here as 0 through F, representing the 4096 number range across here. I've offset our number range by that 4096. So this is the active value range that will be returned by our offset working raw pos. Now, if we look at our current notch position, the one that relates to our current value, this little top hat here up in the middle, it represents where it is. So if the current notch position is here, and then we get our new position, and for example, it's here, it's easy to calculate the distance that we've moved. We've only moved this far, right? If we've moved in a negative direction from the rotation, we can calculate that easy enough as well. We can just calculate the negative value difference here. We could say this is the nominal or the easy outcome case that we can just subtract the values and we'd get the negative or positive differential movement. So the first case I'm going to demonstrate for you. So the current notch is just like I've shown before, but the updated position is basically too high. And what that actually means is that it's actually rolled beyond this scope. It's actually a negative value from a distance perspective. It's actually from here plus here, rotating in a negative direction is the way that we should interpret it. But we can't do that with the simple mathematics. So we have to check if it fits the criteria to be treated in that way. So the criteria would look like something like this. What we actually need to do is we need to have the sum of the distance from the current pointer to the top of the range and the sum of the distance from the bottom of the range to the current value, and that would be the distance, and then we would treat that as a negative component. And the same thing can happen also in the positive direction that we need to deal with as well. So in this case, our new position is actually too low. So in this case, it's actually gone positive. It's actually gone from here, positive up to here, and then wrapped around the different distance to here. So we need to add the distances of those two differential values, add those together, and treat that as a positive component. Yeah, it's a little bit complicated. So I'm just going to leave that there typing. You don't need to type that comment in. I just want to make sure it's clear in your mind. And there we go. So let's write that as code. In effect, the way that we're going to write the code is we're going to check for this case first, and if it's not that case, we'll check for this case, and if it's not this case, then we'll fall back to using the nominal case, and that's the way we're exactly going to write it. So I'm going to actually be dumping the result of the difference traveled into a int 16t value, working value, which will be the working raw difference. So I'm using an integer value so we can have a negative component as a result in this case. First case, this case here that we're going to look at, we just need to see if the current working pos exceeds the current value plus half of a turn. So that's exactly what we're going to write. If the working raw pos, which will be this one here, is greater than the notch raw pos, which plus a half a turn, 2048, then we want to apply this type of mathematics, right? So let's do the result. The working raw diff result would equal to a minus component of the distance between selected notch raw pos minus the base element, 4096, and that'll be another bracket set here just to make it logical, plus 8192 take away working raw pos. Cool, I think it all makes sense. All right, and then we want to do the flip side of it, maybe copy and paste and hopefully not get myself into trouble. So if this is less than the current pos minus 2048, well then we want only to get a positive component, which will be a combination of working raw pos, taking away the base component plus the top value minus the current selected notch position, which is here, okay? And that's not just an if, that should be an else if. Okay, so now we've covered these two nasty cases, and the final thing is that if neither of these two cases apply, well then we're within that sort of easy range, and we can just do a simple subtraction to get the result. So we'll just write another one for that final easy case. Else the working raw diff will be equal to the difference between the working raw pos minus the select notch position, right? Semicolon. I've got the wrong brackets on here because C. So now we have a working raw difference, the distance moved. Now we want to convert that into a number of notches moved. And we're going to use the modulus mathematics symbol just to remove the remainder before we divide it by the raw count per notch. Put simply, all we're doing is dividing it by the number of raw count per notch and getting rid of any fractional component. But as we're working in whole numbers, non-fractional numbers, we want to get rid of that fractional component before we do the division so we get a clean result. The modulus would be working raw diff percent sign for modulus command raw count per notch. So that's going to give us the remainder of any division. So what we're going to do before we do the division is subtract that. So now we have a result here, which is going to be a multiple of this raw count per notch. So when we divide it by raw count per notch, we're going to get a clean division. You know, some people say I'm always speaking too fast, and then people probably say the videos are too long, so yeah, whatever, it is what it is. So, all right, there we go. It's looking pretty good, right? We've managed to figure out what our difference in movement is in raw, then convert that into difference moving in notches. And obviously the notches are the most important things for us because that's what will drive how far we adjust our value. Let me add the comments to this. Okay, so it's interesting to point out that the result, this working notch difference, could actually be zero, right? I mean, if you're only moving the knob just a little bit, then the amount moved could be less than one notch. So it's very, very realistic to expect that the value being returned will be zero movement as far as notches go, and therefore you don't want to adjust your value. There's zero movement of your value. And so we need to check for that before we do anything else. So if it's not equal to zero, only then we're going to start working with the value. So in addition to manipulating the value, which we'll do in a second, the other thing that we need to manipulate is this tracking value, this selected notch raw position. Now you might think we should just set it to be the working raw pos, but that would be a mistake. We actually need to move it by the number of notches that have been moved. And you might think we could just add the number of notches, for example, by doing this. But that also runs into the problem of rolling over in either direction. And once again, because we have that offset in there, we have a safety net. It's never going to roll over so far that it's going to fall beyond the 0 value, because we have that nice 4096 offset in there to keep things positive. We've got to keep things positive here, folks. That's what I'm saying. All right, so the way that we can safety check this is that obviously if it's rolled over beyond the bottom end of the scale, or the 4096, if it's fallen below that, well, then we want to rotate the difference that it's rolled over to the top end. So let's write a little bit of code for that, and I'll let you think about how this works. Okay, so that's going to readjust selected notch raw positive value in the case that it falls below the range, and push it back up into the range. It will roll it back around the other way. And obviously we have the case where it rolls too far forward, so we need to address that case as well. Okay, that should fix our value should it falls outside the range either way. Let me just check the comments in there. So there's a lot more code that we are going to add in here to manipulate the value, especially when we have that min-max range, the rollovers, the acceleration, all that sort of stuff. But right now we're not going to do any of that. We're just going to simply manipulate the value in a very, very simple way. So we're simply going to take the value and add the number of notch movements that have been moved. And if it's negative, it's going to obviously add it in a negative direction. So plus equals working notch difference. And actually that's all we need to do for the value. It's either going to keep rotating forward forever or rotating backwards forever. There's not really any limits that we're doing in this very simplistic version of it. So what we're going to do is we're going to change the meaning of this Boolean result. When we update the value and the value changes, we'll return a positive state, which is what it says. It returns true when the change is made. So if there's no change, we don't want to send back a positive state. So it has to get through this gauntlet of actually having some real value change to actually do that. So we will return back true. So that indicates there's an actual change. And otherwise, I think what I'll do is just return false here. That'll be fine. Just add a comment here. So this is probably going to change a little bit later as we add all the features and functionalities in it. But for now, assuming that the notch actually moves in some direction, it's going to manipulate the value as we see here, and we can send back a true case indicating the value has changed. In our main code, we were looking at the knob update value. So now this is going to be returning positive only if the notch has moved, and we will print the last raw position. What I think I'll do is I will add the raw position and the value so you can sort of see the correlation between the two as well as we work through this. We won't do a print line, we'll do a print, we'll do the raw position, and we'll do another print with a divider, and then we will do a print line, and here we will take a look at the value as we manipulate it. Here's how it works. See if it builds first. It does not build, it's not happy. Oh, sorry, this is the value is actually returned as a variable, not as a function, so we don't want to have that. Hopefully that will fix that. And it surely does. Let's run it. Actually, let me just do one little change here. So we've got this serial print. Because once it initializes, it's not changing. I want to print out that value straight away. And I don't think I care if it fails or not. I think I'll just do it anyway. So let's just print it. So when we do the setup, we're going to just print that same thing. Let's try that again. You'll see now that it's not updating regularly. The programming goes much smoother. Okay, so our raw position is 3041 and our number value is 0. Let's turn the knob and see if we can make a fool of ourselves. Oh, that's nice. So we can see there that it's rotating around quite nicely. But we also notice that some of the number jumps here are quite large. So it's clear that we're missing some. And the reason is because this knob millis is still 250 milliseconds, which I explained to you is not going to be a good result. So let's change this to 25 milliseconds. Try that again. Now we probably won't see any skip numbers. The skip numbers are not actually a problem. It just sort of indicated to me that it was operating so slowly because I wasn't twisting it that fast. It's quite okay that you have jump numbers. You can see you can still jump the numbers. And you'll notice on the left-hand side that the raw number is rolling around and doing its thing. And we can rotate negative and get negative values, and positive values. Let's do one little test. I'm going to put it right here. It's got this little arrow here to the left, and hopefully something like that. I'm going to reset it, and that's going to be our 0 position, which it is. Now if I spin like crazy, we see we go positive. Now I'm going to go back and go back to 0, and you'll see it goes back to the correct position. So that's an indication that we're not losing any steps. Well, you can't lose any steps because it's all locked together in theory, and it works well. So this, as I said, is the primary function. Everything we do after this is easy money, basically. It's just building on top of this fundamental features. And when you're talking about the fundamental features, it's all about managing the relationship between the notches and the rotation of the knob and this weird roll around and wrap around. So if you can understand that, then you've pretty much got this in the bag. That's what it's all about. Everything we do after here is a little bit complicated. It's got a few tricky bits in it, but it's not really the core of what we're doing. So quickly, before we go and start adding a few more bits of functionality, let's test one thing. That is up here, right? We have this other initialization case here, which is it allows us to set a value and a per notch. So we can just see how we can initialize with a specific value and how the different notch sizes affect the outcome. So in the main CPP here, we'll just break it up a little bit. This one here, where we're just initializing with all the defaults, I'll just move that side here. That's the basic initialization. And I have this little bit of test code here, which I'll paste in. So we're going to initialize at the initial value of 100, and we're going to use 16 size notches. Let's run that and just have a look how that works. Okay, initialized at 100, and if we spin the knob, we can see the changes happen pretty quickly. So we can tell that smaller notch is definitely taking effect. And let's try another one. So sure enough, we've initialized with -5, and it should take quite a turn of the knob before we get value changes. So as you can see, finally, yeah, so it's about 1/8 of a turn, which makes sense. Now I'm using fractions, clean fractions of the full range, the 512. And you don't have to, obviously, but in some cases it can be beneficial to actually have a clean division in the single rotation. So generally I sort of stick to it, but as I said, you don't have to. It could just be 500 or 100 or whatever you like. All right, so we've proven that the other initialization type does work. Next up, we're going to use the third initialization type, which has a lot more functionality available, which is the min, max, the rollover, the exponentials and all that sort of stuff, but we're not going to do it all at once, so we'll do it step by step. So in this update value section, which I can find, here it is, before we actually modify the value, we want to add the new functionality. So in this case, we want to say if the range limits are enabled, we'll do something else here. Otherwise, we'll just modify the value normally. Just add my comments in here. So when we're working with the range limits, I'm going to start off by creating a temporary value instead of directly just going ahead and modifying the value like we do down here. So naturally, we need to test that. Else, if the temp value is greater than the max. Otherwise, we're going to have one other case, which is if the value actually doesn't change. This is an else if, and one more else if. Simply return false, indicating no change. And finally, obviously, if the temp value that we've created is inside the min-max range, well, then we can finally go ahead and just set the value as we normally do. I'll just throw in a few comments. Okay, so assuming that we're outside of the valid range, there are two things that can happen. One is that if the rollover is enabled, we're going to shift the value over to the other side, basically, and we'll see that in a second. So I'll add the structure for the rollover enabled part that we'll deal with a little bit later. if there's no rollover, otherwise we're just going to see if the value is already equal to the minimum value, because if the new temp value is less than the min value, then in this non-rollover case we just need that hard stop. We want it to fix at that minimum value. Else if value is not equal to the minimum value, then we'll just force it to be that minimum value. Now, if we aren't setting to the minimum value and we're not doing something in the rollover section, in that case there's no change, so we want to return a false status. Add a few comments. I think that all makes sense. And for on the max side, it should look pretty much the same, right? Max side, we would overflow to the min side on the rollover. No rollover, so make sure the value is set to the max. Yeah, I think that's about it. Already prepared a little bit of test code for this. We'll initialize with 0 and arrange -50 to +50. You can see the initialization values here. The value, the min, the max, rollover defaults to false, per notch will default to 64, etc, etc. So we don't need to do anything with that. We should be able to run it up. Okay, we need it at 0. And roll up to 50. Yep, we got the 50. And it's not doing multiple updates or anything when we get to the end there, which is good. And any sort of fast spinning, it's not like doing anything tricky. It's hitting that end stop quite nice and hard. Even though we hit the end stop, you can see that the 50 position changes, because obviously the notch position is going to vary, even though that the value itself is not varying when we hit the end stop. That's by design. And on the negative side as well, yeah, we hit the 50. Alright, so let's get this rollover going on. The fundamental of the rollover is if we have a temp value which is below the minimum value, then the difference between those two values needs to be moved and rolled around and subtracted from the maximum value. In the simple sort of mathematics, it looks like this. Temp val is equal to the max val, which we'll subtract from the top end of the scale. And what we're going to subtract is minimum value minus temp value. And we need to add 1 to get that number to work correctly with the subtraction. So that's what the math fundamentally looks like, and that should work. But there is a little bit of a problem, and that is that the amount of movement could actually be larger than the minimum and maximum value range, and so you could end up back below where you started. So I implemented a little while loop which just keeps repeating this process until the calculation ends up that the temp value will be above that minimum value. What it is, it's a while. So while the temp value is below, it's meant to be a round bracket. While the temp value is below the minimum value, we'll continue to do this differential subtraction, and eventually it should end up within the valid range. So once we finish getting through this loop, which would typically be only executed, I guess, one time, we can then take that temp value and stick it into our value. I'll just paste in the comments. Yeah, that's good. On the max side of things, it looks pretty much the same. It's a little bit different. Paste it in there. So keep shifting until something comes inside the valid range. That's fine, except we are doing this way. Temp value is greater, so while it's greater than the max value, we're going to shift the difference so it's on the other way around. We shift it around to the minimum side and we add the difference onto there. So it should be min value plus the difference of the temporary value and the max value, and we have to subtract 1 to get that to the numbers to work out correctly. Again, something a little bit ugly here. Alright, let's just see we haven't broken anything first. I'm sure we haven't. Okay, that's working fine. On the main code here, let's make one more with a rollover enabled. So disable this one. We'll go very small range, -5 to 5, and we will enable the rollover. You get it? I think you get it. Let's give it a go. Okay, let's see how we go. 2, 3, 4, 5, -5, so it rolled over. 4, 3, 2, 1, 0, 5, -5. What about the other way? -5, back to 5, -2, -3, -4, -5, rolls over to 5. So that's actually working fine. And let's give it a bit of an aggressive spin, see if we can create some chaos in these numbers. Seems to be 5, 4. I think once you get into this degree of spin, it's sort of really hard to see what's making sense or not. So I'm not sure how effective that little tricky while arrangement works, but in theory it should push it back within the valid range. It makes sense in my mind, but it's a little bit hard to test. Just carrying on from what we were doing in that last section, I didn't like one thing that I had here. These min-max values here, as well as the main value itself, if we look at this H, these are all just free changing values, so the user can change them at any time, and that can create a little bit of chaos in some circumstances. So I like to provide some degree of protection, so I'm going to add one more thing in here to confirm that range limits are enabled. So if the range limits are enabled and the range limits make sense, and that means that the minimum value should be less than the maximum value. And that should do it. So the min value has to be less than the max value for it to be a valid range limit, and obviously the user has to have enabled the range limit. So both those conditions have to be true before we go on and do any of this range limit and therefore rollover stuff as well. So this is just a very minor change. Let's just check it, make sure that we didn't break it. Okay. Yeah, so we have the rollover enabled, but it is working. So the primary basis for the way this is going to function is actually just measuring distance over time. That will give us the speed. Now, we can't really use millis as a fraction of time to measure because that's going to be too large a time span to get a very fine sort of speed measurement. So we're going to have to measure it over micros, which is why when we capture that last raw position, we capture it as micros. And as far as the method of modifying the value that we finally want to adjust, I'm just using a simple multiplier, and it's just a whole number multiplier. It has no fractions. And I'm just doing that to try to keep it as simple as possible. So depending on how fast it's rotating, it'll either be multiplying the change by 1, 2, 3, 4, 5, 6, 7, or 8, or 9 times. So let's get into doing that. I'm going to set up that working multiplier stuff first. And you'll notice I'm using an int16, not an unsigned integer, and that's because we're going to be multiplying against our final value that we're modifying. And if you start mixing the types, you can sometimes lose your sign if you're not careful. And where we'll use that is where we actually are going to modify the value. We actually do it in two locations. Obviously, the one without the range limits here, where we're just adding the working notch difference or the amount of change. So this is where we're going to apply the multiplier. And we also have it up here where we apply the range limits. In this case, we put it in the temporary value first, as we discussed just a little while ago. So we need to apply that multiplier. So what we're going to do now is figure out a way to modify this working multiplier. But as it stands today, obviously it's going to have no effect because we default it as 1. So if user set exponent level is not equal to 0, then we will do the exponential stuff. And we can get straight into it. First thing we're going to do is figure out the amount of time that's passed. So let's put the time span into a working variable. So this last row position micros is obviously gotten when we come in, and we're going to minus last exponential micros. That will give us the time span, and I believe we are setting this when we initialize. Let's just double check that we are. No. So we better do that here. So what we want to do here is just initialize that time measurement value for the exponential. We'll just take a copy of this micros here. just like that. It'd probably work fine even if you didn't initialize it, because we reinitialize it later, but it just makes the micros value that it initializes with a little bit more sensible from a time span measurement perspective, I guess. So here, subtract the exponential micros, or the earlier time, from the newer time to get the amount of duration. And once we've got this working time, we can then go and update this last exponent micros to be the current one as well. So we can use that next time we go ahead and need to measure the time span. So the other part of the equation is knowing the amount of distance moved in this duration. And again, we're going to run into that tricky sort of rollover mathematics, just like we're using and discussed here, to be able to measure that difference. So it looks very, very much the same as this. In fact, why don't we just copy and paste this to save ourselves a bit of time. And we'll just rename a few things. And that should hopefully avoid us making an error. So working raw diff is what I've named it there. And in the code that I originally wrote, I just wrote positive, which is actually a little bit not very descriptive, but it's going to do for this. So it's just this 1, 2, 3, 4 locations that we're going to change. 1, 2, 3, 4. And what we want to check against is not this last selected notch. We want to check against the last exponent position. Now let's have a look at how we initialize that. So let's just replace this first. Last exponent position. And there are 1, 2, 3, 4, 5 of those that we want to change. So 1, 2, 3, 4, 5. And obviously the working raw pos is still the same thing. We still use that offset value, so that's the same. And the only question that remains is how I've initialized this last exponent position. And that initialization of this position obviously has to be done at the same time as we initialize last exponent micros. And obviously it has to be offset as well, just the same as the notch. Now this working pos difference over time, obviously it's distance over time. It's going to be a positive or a negative direction. We don't need the positive and negative direction stuff, so let's neutralize that. Less than 0, then we'll multiply it by -1, which will send us positive, right? So as we now have the distance value and the time value, we can now create a speed value or a distance over time value. And the value that I've decided to work with is per second. So how many raw positions moved within a second is what I want to calculate. So the calculation for that is not that difficult. So working pos diff multiplied by, I'm going to specifically define this as an int 32 so we don't get into trouble. We're going to multiply it by 1,000,000 to turn the microseconds back into seconds, and divide it by working expect duration. So distance over time modified to be equivalent to a 1 second span. So let's make sure this is actually working, that the numbers that we're getting here make sense. We don't have any accessibility to this on the outside, so let's temporarily just stick something here. Just make something public. Take a copy of that value. Oh, I forgot my semicolon here. Alright, so we can take a look at this. I'll stick it here for a second. It will allow us to have a peek at this value here, and it's not a function, so get rid of that. Now we could add the enabling for the exponential in the initializer, but we can also enable it externally of that. I'll just set it at 1. It doesn't really matter because we're not doing anything with the level value at the moment, but it will enable it and allow us to get that calculation to be working. And I'll just stick it here. Okay. So we'll just do a very simple initialize with a fairly small notches. But I'm using the small notches so we get a frequent update, so we can actually see the acceleration or the speed that we're moving the knob. Hopefully we're going to get something that makes sense. Okay. Well, the number doesn't make sense, right? So why is that? I'm wondering if any of you guys can see why that might be the case. Yep, I'm thinking one or two of you might have picked it out. So up here, we are calculating the time duration, and here we are saving the last time duration, or updating the last time duration here. And here we're modifying the distance duration, but we're not actually saving the last position. So obviously the calculation is going to be all thrown off. So let's fix that little bug. We need to save the last position with this current working raw pos. Okay, so that should hopefully fix it. Let's upload that and check it. Okay, so if I go very slowly, we can see that it's like 40 raw positions per second, and a little bit faster, 80. It's quite granular. But as I go faster, we can see faster and faster. And if I really go fast, what are the biggest numbers we can see? Like about 17, 18,000. And if we go in the negative direction, again, slowly, 40s and 80s. And if I go really fast. So anyway, the key point is that we have a number that seems to make sense and relates to the speed of the knob, and we can use that now to generate our multiplier. So let's do that. I think I want to get rid of this temporary working garbage as well, otherwise I'll forget later. So now we have to manipulate our working multiplier based upon the speed. So anyway, I came up with this bit of mathematics to sort of figure out a way to add this multiplication, and I just did it by experimentation. I don't really love this. There's probably a better way to do this, and you're free to do that too. Think about it more. For me, it sort of works good enough, and this is what I settled with. But first off is I do a basic setup of the working multiplier. So this working multiplier that I'm working on here is not the actual multiplier that we use in the end. This is actually a representation of speed of working positions per second, something that I can use to compare against this. And after I do the comparison, I will then come up with the final working multipliers. Anyway, let's do that, and you can sort of see how that might work. So if the speed is less than this working speed, then I'm not going to do any multiplication. So the actual working multiplier that we use will simply set to 1. So yeah, this first one here is just the slowest speed, and then I have increasing speeds. The faster it is, the bigger the multiplier. So for example, else if, and if the speed was twice as fast as this working reference speed that we worked out, then the multiplier would be 2. Okay, and so on. And this last fallout case. So if it's 2 times faster, multiplies 2, 3, 4, 5, 6, 7, 8. Yeah, it's very, very not elegant is probably the best way to pull it, but it will do the job. And if it's faster than 8 times this working speed that I figured out, well then it will always be 9. That's the biggest multiplier that I can return, basically. Alright, hope that makes sense. You put in the comments. So I just pasted in my code from my original area to get this comment, and obviously I can't spell multiplier consistently. That's why we have this error here. Let me just fix this here. Maybe I'll just replace multiplier with multiplier. Hopefully that will get the error to go away. And yeah, our error's gone away. Now, will it build? It will not. Oh yes, so we still have this bit of garbage left here. We don't need that anymore. For this test, I'm just going to go ahead and start messing with the exponent level that we're using, and we'll do a little comparison to see how that affects our value. So exponent level 0, 1, 2, 3. We got up to 457 with some quickish spins, which is directly tied to the position of the knob in this case. There's no acceleration based adjustment. Exponent level 1. Yeah, you can see that's really crazy, right? So you can see I'm getting that fine adjustments with the small movements, so we can select any value, but we can move quite a long way fairly quickly with these fine notches with this even very low level exponential. Okay, for this last bit, we're going to actually create a physical lock between the knob and the value. So there are some limitations to the way that I'm implementing this. One is that the notch size that you use has to be nice and even division whole number of the total 4096 range. There are a bunch of other sort of rules sort of limiting the use of it so it doesn't break it. Let's just say, like everything in here, it's a little bit complicated. Do later. Set value to raw position. So this is where we apply it in this initialization. So if the value is provided, it will apply it, or alternatively we could use this function separately. This is defaulted to 4096, so anything above 4095 will effectively disable this feature. Let's go and have a look at what we've got in this little function. And yeah, we got a big fat nothing. Big fat nothing. Let's get it done. So the first little rule of it all is that range limits and the min-max value settings must be made for this to work. Min value is greater than or equal to the max value. Rollover must also be enabled. Exponential is not allowed. So next up, it's going to look at the minimum maximum range and make sure that the number of values that would exist in a single full rotation based upon your notch size is equal to the full range. And we're going to multiply that range by the raw count per notch. No, I got the wrong brackets here. Yeah, min minus x plus 1 times raw count per notch, not equal to 1 and then return false. Okay, so that makes sure that our range covers that 4096 full. And we want to make sure this provided value is within this range, otherwise it'll be disabled, obviously. Probably could do that earlier, but I'll just do it down here anyway. Okay, I add the comments here. And now we're actually getting into actually doing the actual code related to this. And the first thing I'm going to do is reread the position. So we'll just take it straight from the initialize. So it's literally a portion of this initialize that we're going to redo. And same with the init. Actually, I probably should have just taken a bit more. We'll take this as well. So I'm not messing with that exponential values or saving any of those other values here. I'm just going to create a little working value, taking a copy of that last raw position. So let's talk about what we've got and what it sort of looks like first so we can understand what it is. The range, this is like the full range here of the AS5600, 4096 as I've represented from 0 to F here. The minimum value raw position that we've been provided is going to be somewhere within this range. And then we have this detected working raw pos, which in theory is meant to represent a specific value at a specific notch. The simple way to look at it would be, for example, this. We have the detected working value and we want to know the distance between here and here in notch counts. You could say each of these digits would represent a notch count, and we could just simply count the number of notches there are and figure out the resultant value. I mean, that's basically what we need to do. There is a bit of a fly in the ointment, however, because obviously it's never that easy with these stuff. If we have a minimum raw value position which is above the detected working raw pos, effectively we need to count the number of units forward from here to here and rotating back around again. What I do is I add one entire rotation to this detected working raw pos. full rotation or 16 characters here in this case that I move the value forward, and then I do this simple count process to count the number of notches, and that gives you the same result. And the other thing that we have an issue with is that the current position in relation to the notches will be somewhere usually in the middle between two notches, and it's either on one notch or the other notch, so we need to figure out which specific notch that is as well. So that's the basics of it. The first thing we need to do is deal with this case where it's reversed basically. So let's start off by doing that. Alright, as I said, I'm not going to use some tricky mathematics. I'm actually going to use a window-based forward-moving search with a while. So we need to start off by initializing our other variables that we will move forward as we search forward. So I'm going to take a copy of what the start point is, or this min val raw pos is. And also need to create a working value that we can increase as we move forward until we drop into the window. And obviously it's going to start off at the minimum value. And the while is going to go for as long as the working value remains below or equivalent to the maximum value. So we'll keep moving that working value forward up until it hits the max value at least. In theory, it shouldn't actually ever make use of this condition. It should actually resolve itself without any condition. So you probably could leave this just empty, but I just do this for safety, especially when you're coding and debugging something. You want to have a safety exit condition so it doesn't just get stuck in a conditional loop in a bug type scenario. That's going to make it easier to debug your code, that's for sure. So we need to do a check to see if that working raw pos is actually falling into that forward moving window, and that's going to look like this. The working raw pos is greater than or equal to the current position of the search raw pos, the value that's moving forward, and is below the window of the search raw pos, which is the search raw pos plus the size of the window, which is the number of raw count per notch. So if we find this to be true, then obviously the working raw pos is actually inside the window here. And if it's not true, well then we need to keep moving things forward, right? Forward would mean shifting the working value forward and shifting the search position forward by a notch at a time. So that's the basic of the search, right? This is moving it forward, and this is checking to see if we fall within that valid window. So once we've discovered our current raw position is within the window, it's still a little bit complicated what we need to do, because we need to decide if we are closer to the lower end of the window or the upper end of the window. If we're at the lower end of the window, the value can just remain the value that we're working with. But if we're at the upper end of the window, we actually need to shift the value up by 1. So I came up with this little formula here to try to make it hopefully a little bit easier to understand how we're going to figure out if we're closer to the lower end of the window or the upper end of the window. We do it by looking at the distance of the current working raw position in relation to the lower bracket. If the distance between the lower bracket is larger than the distance to the upper bracket, if the value is further along, closer to the upper bracket, well then we want to use the upper notch. We can actually just write it by taking this and substituting some values. To use the upper notch, obviously the value itself is currently pointing or being increased in relation to the lower notch, so we need to increase this working value by 1. But we also need to shift the search raw position up so that it's pointing towards the upper bracket as well. And we'll move it by 1 entire notch, right? Okay, so that will solve the problem as to figuring out which side of the window that we are falling on. One other thing that we need to solve is the fact that this search raw pos might be above the valid range because we shifted it up by 4096. So we'll just renormalize that, and we can just check it by saying if the search raw pos greater than 4095, in other words beyond the valid range, then we know it's moving into that forward search position. So we can rectify that simply by minus equaling 4096, so removing this offset that we added here in the search. And there's one more thing that we need to add here, and it specifically relates to what we're doing here. there is a scenario where we are right at the end of the window where we're moving this working value forward. And say, for example, the value was between 1 and 16, and we had kept moving this value forward and found that the working value resulted in a value of 16, which was right at the end of the max value. But it's also found that the position of the working roll pos is closer to the upper end of the window. And that will actually mean that this value will be pushed to 17, for example. So effectively that means it's going to have rolled over to the minimum value. It should have rolled over, but it can't roll over because it's just kept moving forward. So in this case, we need to address that scenario as well. If the working value has now exceeded the max value, in that case, we want to take that working value and roll it over. And we do that by subtracting the amount of the max value, basically. Okay, so that should address that rollover case. And just looking at this code, I'm a little bit nervous that it might be the case that there are more than one unit of this. So I'm going to actually just change this to a while. I don't think it should happen, but I don't want to think it through, and I know that was going to solve the problem. So now that we've figured out the final working value and the raw position, we can actually save those values in our actual values that we'll update going forward. So as we've got this far, everything's worked out well, and we can send back a positive indication that we've succeeded in setting up this relationship. So that's quite a lot of code, so hopefully that's going to work. And just one other thing, in theory we should never get this far. I guess it could be some sort of weird situation. Just make sure we return false if all else fails. Okay, so the initial part is making sure everything is in a state that allows us to set up the relationship. We set up our working values, and we search through using Windows-based search. We modify and fix some of the values, and then we set our final values and send back a positive state. Okay, let's see if it'll build. Builds okay. So let's set up another test scenario. So let's start off with 1. And as we know, for this to work, we need to have a quantity of values, which means the sum of the notches for the entire value range equals the same as 1 rotation. So if we have 16 values, we would need notches the size of 256. We're going to go 1 through 16, starting at 1. We need to roll over for this to be enabled. Per notch, 256. I can keep going and we can actually set up that minimum relative pos, but I'm not going to do it here. First I want to just test that this is working. Alright. Oh, here's the old set exponential level, which I'll get rid of here. So start with 1 through 16, enable the rollover, 256. Let's just see that that's working first. So you can see we've started off and we're pointing up this way. I think that's up in your direction too. And as we rotate around, and then 1. Okay, so we're back in the same position. So it doesn't matter how much we rotate, this position here is always going to be 1. And if I reset it, now this is 1. So this is not locked, right? We don't have any physical relationship between the knob and the values that we're getting back. But say, for example, I want to have always this left-hand arrow pointing this way. I always want to have that to be set up as 1. And that's the relationship we want to configure. So right now we can see on the screen there that we're getting 9, but we can see that it's 2,318. Let's just use that number, that 2,318. What I'll do is add a check code, right, just to make sure that we can set it up. So we need to put the raw pos for the minimum value, and in this case we said we're going to go with that 2318. So this is similar to what we've got up here. We're going to initialize with the same settings. And what I might do is just repeat this so we can see what those original values will look like. Then we'll set that relationship, locking 1 to be equivalent to the raw position of 2318. And this should tell us if it succeeded or not. And then we'll update the first value with what that post modification looks like. So it initialized OK and it set the relationship OK, even though our number is a little bit different to what we expected. I think one of the reasons is because we don't know what that raw position is. So let's move it to the position we want and reset. And the raw position is 2479. So that will be our position for 1. Okay, so this left-hand side is our position for 1. And we can rotate it around. Now, as you can see, as I've rotated around, I'm at position 7 now. If I reset, it would have initialized at 4018 being position 1, but it set the relationship and it's retrieved the 7. So if I go and rotate, now I've changed to 5, reset, 5. So now I'm rotating, I've just hit 6, reset, we've got 6. And this time I'm going to rotate to 7. And then just go a bit further before we get to 8. So we're pretty much closer to 8 now than we are to 7, but we haven't clicked into it. But after resetting it, we're still on 7. At some point, it will probably carry over to that next number. So we haven't got to 8 yet. So yeah, we're 8. So we were at 7, and we've switched to 8. That's because we haven't actually fallen into that notch yet when we're rotating it. So I don't know if that's, it's not perfect in the sense that you reboot and you get the same value you had just before, because the logic is a little bit different between the realignment and the notch selection mechanism. But I think for most cases, it's probably going to be fine. I mean, if you had big red dots on your scale and people were turning to, or you had a notched button where it was actually falling into those slots with some sort of physical impediment, then obviously it would always be right. But when we have this free range movement, obviously we're going to have a little bit of that difference. And obviously that's also going to be related to the size of your notches as well. Okay, so I've completed that. I've got this new copy of the folder that we made in that last episode. I've also added the AS5600 notched folder here with the CPP and the H. So ready to go. Let's just plug in this display. Let's upload that, see if we can get the old menu working. So there it is on the screen here. Got it lined up so you can see it. Seems to be working. Obviously we don't have the 6 buttons anymore. We only have 2 buttons, the OK and the cancel. And as you can see, those buttons are still working. Other than that, all the other buttons are not connected, but right now the code is just as it was, so obviously it's going to be not working because we've got no way of navigating. We can't roll the knob here or do anything. We'll start up by addressing the menu navigation stuff. The first thing we want to do is include our new custom class. So we'll stick it below the include press button. Now we've got all these unwanted buttons here. I mean, we can delete them a little bit later. You can see all these buttons. But if we delete them now, it's going to create errors. So we'll just leave them there. You can delete them at your leisure. We need to initialize or declare our little AS5600 in the init section here somewhere. And just as we did before, we'll use the default wire, so we don't need to do anything else. For the setup, we don't actually need to do anything, because every time we go into a menu, we'll effectively be setting up the knob the way that we need it to work. So the great thing about this last menu that we made is that a lot of the functions, the way it works, all have been made pretty common. So we only need to adjust it in that one location. So a quick look through this code. Most of the stuff we can leave alone. Obviously we probably could get rid of some of this stuff here. Just leave it for now. What we want to do is add the initialization for the knob. We'll do it here, I guess. And we'll initialize it at the value of the pointer position. Value which is pointing to where the current pointer is in relation to the items in the menu. So we use that. And as you can see, this is where we're actually configuring that, resetting that to be 1 here. So it's going to be 1 in any case. So we'll set it up as a range from 1 through to the number of items, item count. I'm going to disable the rollover. Obviously we could just leave that, but I'm not, because I want to change the per notch count. So I have to set the rollover value as well. And I'm going to go with 128, fairly largish sort of notch sizes. I'll also demonstrate a few other ways of doing this initialization, but let's just start off with a simple one first. What else have we got in here? Do pointer navigation. Yeah, that's going to be important. I think we need to look at that. So move pointer up means that we're reducing the pointer size. So obviously we don't have an up button anymore, so we better get rid of that. Same here with the down as well. We don't have down. So what we can do is just do a quick comparison against the pointer pos and the knob value. So if the knob value is less than the pointer pos, then we'll reduce the position of the pointer. And it could be a case where the knob value is a lot less than just one value, because if you scroll it really quick, it could actually move quite a few elements. But if that's the case, the pointer navigation will enter again and continue to reduce the pointer pos until it equals or is no longer greater than the knob value. And on the flip side, the other direction, so as long as the knob value is less than and equal to item counts, and then similar to above if the knob value is greater than the pointer pos. That's probably about it, right? Yeah, so in effect we actually have two values. We have the actual pointer pos and we have the knob value, and the pointer pos is always trying to chase after the position that the knob value is currently set. I think that is easier to implement. I mean, there could be a scenario where we actually just use the knob value, but it's going to make it a little bit harder to implement in here, and it creates all sorts of problems. So this chasing effect is as good as any other way to implement this, I believe. I wonder if that'll work. Let's give it a try. Oh, well, no, there's obviously something we've forgotten. So we're not actually updating the value anywhere. So obviously that has to be done. So where should we update the value? We want to do it every 25 milliseconds. So we should do it in the pacing wait. So here we're pacing waiting. Right at the end of the pacing, which is 25 milliseconds, which is nice and handy, we will do that knob update just before we get into the code. I think that'll be as good as any place to do it. So this is where we're going to go out and get that new value. All right, let's see if we have a little bit more success. Oh, there you go, look at that. So just with that little bit of code modification, we now have a knob that's working. We go into the second submenu, yeah, up and down, and nothing in here, back. So that's it really. I wanted to demonstrate, however, two other types of ways to implement this, and I don't think they're specifically good ways to implement it, but just to show you an example of how this actually works. So I'm just going to copy and paste them in just to save a little bit of time. Here are the three examples that I had come up with. This is the one that we just did now, the basic one. Now let's try one with rollover. So it's basically the same except we have the rollover enabled. So when we get to the top, it should go to the bottom again. Let's try this. Should be pretty easy to test. Okay. Down. So at the bottom, and then roll around, and we're back at the top. So there's the rollover, and we can roll over the other way. So I think it's not an unusable, I mean, you might want to use this in some situations, but I don't really like it all that much. And the other one is fixed position, which again, I don't think is ideal. And I'm just looking at the minimum value, or position 1, to this 2515 position, which I believe was over to the left here. Let's try this one. So there's menu item 1 at the left here, 2, 3, 4, and if I reset, it's gone a little bit below, but same thing, right? 3, 2, 1 at the top, so it's maintaining a physical lock, or somewhat physical lock, to the position. And if we rotate well beyond and rotate back around, we get back to 1 and it pushes to 1. So that's where we have a physical position lock. I think it's okay. Alright, so let me get rid of this and go back to the basic one, the simple one, because as I said, I think that makes more sense. Alright, nice and good. Next up, we're actually going to start trying to manipulate these values. If we go down to the settings, and you can see all those values, we want to be able to modify the values. Because we don't have a separate up or down buttons, we have to get into an editing mode. So we have to create a new editing mode. And I've done this before in some other applications you might have seen that I've made, such as the UV timer box. Similar sort of thing, you have to sort of layer your actions. So what I want to do is press enter to get in and edit a value, change the value, and I want to have the ability to enter again to save it, or escape to undo the change. So that's what we're going to do. Okay, so we're looking at the code for that settings page, and I think you're going to have to bear with me for a little bit here for a second as we work through it. It's not that straightforward as you might expect. One of the first things that I have to consider about this is how I'm setting these defaults. So in that last episode, we're using a long press of the OK, but in this new menu, we're going to be using the OK button to begin the editing and the cancel button to do the undo, which is fine. But in the last episode, when we pressed the OK, it didn't do anything else. So long pressing it didn't risk having any confusion between short or long press. But in this case, the OK is also going to be initiating editing. So I didn't really like that much. So what I decided to do was change it to a multi-press. So the idea would be that you would press the middle of the button here, which engages both the OK and the cancel together, and that would set your defaults. Obviously it's doing something different there. So that's what we're going to do first. Get that out of the way, and then we'll move on to the editing stuff. So I've shown how to do this multi-press stuff before. For now, however, we do need to track if we are in the process of being multi-pressed as a part of the logic tree. So we'll have a variable for that. Has multi-pressed, and default that to being null, of course. And then right up until button stage, we need to start working on the logic for the multi-pressing. So if we haven't already detected the multi-pressed state yet, and button OK is down, and button back is also down, well then we can initiate the multi-press action. And that's basically just going to be doing that restore defaults stuff, which is this. And as we don't want to do this more than once we executed the multi-press action, we want to make sure we don't come back in again here until that state is fully cleared. So it has multi-pressed equals true. And that will lock us out from coming back in here until that's cleared. So the next case that we need to consider is that the multi-press is still in progress, but we're not repeating this action, obviously. So we're in that holding state where the buttons are still down. We have to keep monitoring and wait for both of those buttons to be released before going back into the normal state, basically, of just waiting for single button press. So if we have multi-pressed, now we want to make sure, or check to see that both buttons go back up. I'll just copy this. Now, as this multi-press stuff is all pretty manual, we need to manually get here and do a few things, which is to clear those was down states to get back to a normal state. And I did notice that there is an oversight in this here that I wanted to add. So we're going to go and have a look at this clear was down code. And yeah, that's just clearing the was down code. But actually, alongside of this, I also want to clear the repeat count as well, just to get everything back onto an even keel, similar to as if we had like press release, right? So we'll just add that in here as well. And I'll make a little notation of that. And in the .h file. Okay, so that's the only thing I added to the press button class. So we clear the button states for the up and down. We can also go ahead and clear this multi-press state, because we're coming out of multi-press. And as that knob might have actually been moving or rotating during the multi-press period, could actually cause some shifting. So what we'll do is reinitialize that knob as well back to a 0 type state, just to get it also back on an even keel as well. And I'll just copy and paste it. It's probably safer, right? Just copy and paste that. Like that. Clear the button states, clear the multi-press state, and oh, this item count here is locked, initialized. So that will get us in and out of the multi-press state. Now we can go on to handling the normal state. And I'll just put our lockout on the multi-press here as well, so we don't try to come in here while we're in the multi-press state. So what are we going to have in here? Obviously, capturing the button states is something we can do. This getting out. And add one more condition here. So if we don't go back, we can just do this pointer navigation. Keep pressing the wrong brackets. And this old switch pointer action editing stuff and this long press stuff, we don't actually need that for now. I'm just going to comment that out. Alright, well, let's just see if this multi-pressing is working, and if we still get out, yeah, it should be fine. Alright, let's give it a go. Yeah, there's not really any way to test it because I can't change the values. We should be able to see if we can go back. We can still go back, that's good. Well, that's weird. Back. Why is it returning it there? Should return it to the root value, right? Sorry, a little bit of a distraction here. Oh, I see. We are modifying the display offset and the pointer pause here, which we were saving. So we were saving those as we leave here, and we were recalling them here, but actually we need to include that in this init menu page section. So let's do that. We'll give it the pointer we want and the offset we want, and we'll delete that. Now we have a declaration, I guess, for this menu page up here with those two new items here that we're going to add. We're going to specify the pointer that it wants to start with and the offset that we want it to start with now. So we can add those here as a U int 8t, the pointer we want, and the U int 8t, the offset we want. Now it's going to be a real pain to go back in and modify all of the different menus because only the root menu uses, you know, the recall of the pointer and the offset. So the great thing about this, as we used in the class as well, we can use defaults. So we can default this to be equal to 1 if it's not specified, and we'll default the offset to equal to 0 if it's not specified, which is fine. But we need to go and also fix the actual routine. You can see now it's got this little dot 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 there because it's not matching. Control F. So originally it was only the title and the item count, but now we're also adding the pointer, which will be defaulted, and the offset. And the question is how we use those. Well, it's pretty straightforward. Here I'm actually forcing them to be 1 and 0, which is why we were seeing that behavior that we didn't want to see. So the pointer pos can be equal to the pointer that's provided, which will default to 1, and the offset will be set to the offset that was provided, which will also set to 0, so no offset. All right, let's go back and try that again. So if we go into our settings and then back out, yeah, we have the offset correct, and we have the pointer correct for that root menu, which is the behavior we had achieved in that last episode. Unfortunately, I can multi-press this, at least confirm that it's not doing anything weird. I can turn the knob around and release it, and it behaves without any abnormality, but it's actually resetting the defaults, but we can't see that because we can't change any values. But otherwise it seems to return back to normal and everything else is working. All right. In this next section we need to get into the editing mode. All right, so right now we just have this normal navigation or item selection section of code and the ability to exit and the ability to restore the defaults. We don't have the ability to edit. And in this case, I want to edit into an editing mode and flash the specific value. Stop flashing the pointer and start flashing the value. I don't want to flash the pointer and the value. I mean, I could do that, but it'd be really annoying. So we'll just flash the editing value. So similar to multi-press, we're going to have a flag again that will track if we're in the editing mode or not. Initially, we're going to start in a non-editing mode. And we're basically going to split up the functional mode here from the navigation section and the editing section. Even the display section here we won't keep. So as soon as we get into the loop here, we'll split off. If we're not editing, then we can do all of this stuff. Pacing weight can remain common. Tabulate that in one. So if we're not editing, then do the item selection navigation. Down to here. Otherwise, we're in that editing section, right? We're actually in the editing mode, which will function a little bit differently. Now, obviously, we need a way to get into the editing mode for the specific value, so we need to set that up. So just after we give the check to see if it's time to get out, we'll also do a check to see if it's time to edit. So else if button OK was press release. Well, then we're going to enter the editing mode for the current selected item. What is that bracket? That bracket, okay. Now, as I want to have the ability to undo, I'm going to make a copy of the settings, and we need somewhere to put that. So I'll just declare it at the top here. Make another version of the my settings type structure. And this will be the copy that we'll use for editing. So this is where we'll change it, and we'll only apply or switch it out once we commit to the changes, basically. All right, so that's the object we're going to work with, this edit sets, and we'll use memcopy to make a copy of it. Memcopy, the target will be edit set, and we'll take a copy of the current settings, take a whole copy of the entire settings, size of the amount of bytes we want to copy. And it doesn't matter which object we refer to, so we'll just size of settings because they're both the same type and therefore they're both the same size. And as we enter the editing mode, the other thing I want to do is hide the pointer because it was flashing there, right, indicating which one we're editing, but I don't want to have it sort of sitting there on. So to do that, I will set the flash on to be false. You set the flash counter to be at the rollover point. And then you call on it to print the pointer, and that'll immediately print it to the clear state. Print pointer. And now we need to set the editing mode. And the final thing we need to do is initialize the navigation knob in a way that makes sense for the type of setting we're dealing with. So we only have two types of settings as per this original sort of code here. It's either Boolean type or 0 to 255 settings. Obviously we could do that differently, but that's the way we were doing it here. So I'm just going to replicate that behavior. Obviously in a real world scenario, you would do whatever makes sense for a specific setting type. So based upon the pointer pos, we will decide all of these cases. So case 1, we will do a knob and initialize using the value in the edit set. Yeah, on off, so that's a boolean. And the value will switch between 0 and 1 on and off. I won't do any rollover. I'll use a pretty large step, 256. And then we need to add break at the end of each of the cases. All right, so for case 2, num 0 to 255, rollover false, 64 per notch rate. And I'm going to enable the exponential on this just to add a bit of flavor so we can see that in use in a practical case. So I'll have a fairly aggressive level of exponential. 3, 4, also numbers, and I'm just doing the same thing. As I said, you can make these any way you like. I'm just a little bit lazy to give a mix of examples. Case 5 is also Boolean. The 6th setting again was a number. So let's just review. If we have an OK press release, take a copy of the settings, turn the pointer off, we'll get ourselves in the editing mode, and we'll set up the knob for the given setting and initialize it with the current setting value. And that's about it. I wonder if we should test that. It's only going to get stuck here, but at a bare minimum, we should at least see that the pointer will be switched off. Let's have a look quickly. Have some error. Too few arguments. Oh, what is that? CCP, I spelled this wrong. There must be another version. Apparently there's another routine called MCCPY. Okay, anyway, that's debugging for you. Go to the settings and you can navigate, select any of them, yes, and yeah, let's do it one more time. Should be on the release, right? Press and release. Check for that. So press down, still flashing, and release. Yeah, it's gone. And obviously frozen, just what you would expect. So okay, so now we're getting into the editing mode. Now we need to handle that editing state. I think what we'll start off with is flashing the specific value. And we can just use this, where is it? This use flash change stuff as a part of the process. In this editing section, if flash change, and we're also going to be modifying the value. So we'd want to reprint it when the value changes, or if there's a flash change, or if we want to flash it. So there's two cases where we'll reprint it. If it's flash changed, or we have a request to update the item value. And this is where it gets a little bit tricky. What we want to do is locate the cursor in the right place with relation to the offset for the specific pointer, but it's complicated, right? And thankfully we have a routine that sort of addresses that. This menu item printable not only gives you a true state if the item's on the screen, it also locates the cursor for you. So we can reuse that. It's going to save a little bit of work. So menu item printer, we don't need an if case, we just want to locate the cursor at the pointer pause. So it'll locate it at 14 and to the pointer pause, and it will apply the offset. Let's have a quick look at that, right? So it looks like it's not going to do anything if some basic conditions aren't met. Update our items we're not going to set, but we are going to set update item value, but we're only going to set that when we change the value, so not in the flashing case. So that's going to be a problem. It's not going to locate the cursor for us. What we can do is we can force this update item value to be true, and that will force it to do that cursor location for us. So let's do that as a part of this function. Equals true. So it's only going to come in here if that's true, or if it's flashed. But either way, we're then going to force it to be true and make sure it locates the cursor for us. All right, that works well. Now, depending on the flash state, we'll either print a blank, cover it up, or we will print the specific value at the given location. So if it's flash is on, then LCD print 1, 2, 3, 4, 5 spaces. That will give us that blank result, and I gotta get a semicolon in here. All right. Otherwise, we're gonna print the actual value depending on the case. So else. All right. Let's add some comments up to there. Yeah, I thought I lost a bracket there somewhere. So otherwise, print the value of the selected item to the screen. So we have up here where we're printing the values, so we just want to repeat that, I guess, or take part of that. But we want to do it on a switched case, so let's switch it like this. But print it like this. So this will be the first one. So get rid of this bit of garbage. And we need the end of the bracket here. Is that right? Ooh, I stuck it in the wrong place. Let me copy that and just undo all of my garbage. Sorry, is that confusing? Sorry, I stuck it in the wrong section. Undo all that. Okay, this is where we wanted to stick it, so stick it here. And we've got all the right break. I didn't break anything, right? This is still okay up here. This is getting us into the setup for the editing for the specific item. And this is printing the current editing item. I do notice one mistake though, because we're meant to be working with the edit sets, right? And here I'm displaying or printing the active settings. So let's switch this to the edit sets. So this will be the entirety of the flashing cycle, which is to clear it and print it, clear it and print it, clear it and print it, or the update item depending if it's requested to be updated. Actually, we need to clear this update state on the way out, otherwise it will perpetually be set and continually updating. And fix this little copy paste bug here. Yeah. So now we can hopefully flash the item, right? Let's see how that goes. Down to the settings, select the second one. The cursor is gone and the value is flashing, but obviously nothing else works. Let's just try an offsetted one as well, just to be sure that it's working okay. Settings, go down to the bottom. That's flashing fine, all right. So that's working. All right, let's add the button actions. So after we do the printing stuff, we'll do it just below that. We need to, just as we would do with the navigation, we need to capture the button down states. And if it's back or okay, there's two states we need to check. So if it's button back, press released, then we need to do something. Otherwise, if it's button okay, press released. And the pacing weight is down here outside of that, so we don't need to worry about that. Obviously that was working before with the flashing, we saw that was working. So let's add a few comments onto that. So if it's back, we're just gonna simply exit and not bother saving any of the changes. If we are okay, we want to save those changes in those editing setting sets before we exit back into the normal state. In both cases, obviously we're gonna have to reset up the knob so that it's functioning correctly. Yeah, so let's do that. Set it back to the pointer pause for the range of 1 through 6, false, and 128. Okay. We'll set the flash so the pointer will come on quickly. We'll disable the editing mode and we'll force an update on the current item, because it could be the case that it was hidden when we actually exit this state. That will ensure that it gets reprinted on the screen. And for the OK, it's basically all of this again. There's probably a better way to have written it code-wise, but anyway. However, we need to save the settings before we exit the edit mode. And that is literally just, you know, something which looks like this, right? The reverse of this, I guess you would say. So actually, instead of moving the settings into the edit sets, we're moving the edit sets into the settings. All right, does that make sense? Now, obviously we can't modify the value, so once again, we're not going to be able to see the effect of this save being made, but at least we can just see the functionality is working let me add the comments. Alrighty, I think we're ready to go for the next test round. I've sort of half forgotten what we're meant to be testing. Entering and exiting the editing mode, okay? Get into the editing mode. We can't modify the value. We can exit the editing mode with the OK. Yeah. Let's repeat that a few times. In, out, yep, it's not disappearing, and in and out with the exit. Same thing, right? Of course, because it's basically the same code, except one has the save and one doesn't have the save. All right, finally we get to modify the values, and I'm actually going to modify the values before we print the values. I think that makes more sense, right? And we can actually just take this code here and maybe just repeat it. Let's get rid of this long press garbage. We'll take this. Throw it up here. And get it in the right tab positions. Must be after. I think this is old stuff, right? Anyway, whatever, just ignore that comment. It's just a recycled comment. Alright, let's have a look at what we've got here. Adjust Boolean, obviously with the old method. Adjust uint8, they're the only functions that we have. Now, I have noticed that we have this range stuff here provided for the uint8, but the range is now going to be controlled by the function of the knob itself. So we don't need that. Otherwise, we can pretty much reuse it as it is. One, two, three, four. Okay, I've lost it now. Menu settings. Oh yeah, so we've got an error here. So let's just fix those two functions so that they work with the knob. So the adjust int, we don't need that range, and obviously that's going to have an error at the top here as well, where we define it, because we have to double define everything in C, like idiots. So for the Boolean, for example, how are we going to do this? Well, all of this stuff is basically garbage. We want to adjust this value based upon the knob. So if the value, reference value, but the value is not equal to what the knob currently is, not equal to, and the knob is going to be 0 and 1, so we need to convert that to a Boolean for comparison. Probably don't need to convert it, but probably it's more explicit to and safer to be specifying conversions, I guess. Knob.value. So if the value is not equal to the knob value, well, the obvious thing to do would be to make the value equal the knob value. And yeah, we also need to reprint that value on the screen as we change it. So we need to force a update item value. Flash is on equals true. And flash counter equals 0. I haven't done it here. Equals true. Alright, so it's pretty straightforward, right? We're just basically taking the knob value directly. We're not chasing the value in this case, we're just directly setting the value. So that's a little bit different to what we're doing with the menus. So also for the uint8, or any other value for that matter, we can pretty much do exactly the same thing, right? Except all this stuff is uint8. We'll just do the conversion. What do you reckon? I reckon that looks about it. Makes me get all worried when it's that easy. There's always something else there waiting to bite you in the bum. Alright. Build. Does it work? Let's try it out. Settings. Get into edit mode. Oh. The value is not changing. What sort of a bug have I created, folks? Yeah. Oh my god. I'm working in the edit sets, not in the settings. Here we go. Dumber and dumber at your doorstep. Here you go. Let's try that. Settings. We'll go for a third one, for third time lucky. It's totally irrelevant. Roll it up, it doesn't go up. Roll it down. Oh, and the value changes. It's a small miracle, right? One at a time, or if we really crank up quick, you can do the whole range in one quick spin, right? And that can't be done with an up and down button, that's for sure. Look at that. So we can quickly move up and down the number range and still get to, say, 150. Boom, 150, no problem. And I will undo. Immediately undoes. What about a save? 234, okay, saved. Back out, back in, 234. What about the logic values? On, off, back out, save the change, back out, back in, yeah. What about restore defaults? Press in the middle, so the multi-press, and the values have immediately all changed. I noticed it's not based upon the release. Once you press it, it's have a nice day, you're all done. Well, there's no exit anyway, so that makes sense, right? And back out, back in. Yep, the defaults have been saved, set and saved. It's a little bit. I'm not sure I'd actually do it that way in a real code. I think I'd add another layer of saying, "Are you sure you want to restore the defaults?" or something like that. But I'm not really demonstrating fully practical code here. I'm just trying to demonstrate ways of doing things. This one. I don't see anything not working as expected. And back in. Back out, back in, whatever, restore defaults. And the point is you can also twist the number around, but once you release, it will also stay where it was, so it doesn't get any negative effect. And that's it, my folks. I hope it was a useful lesson for you. It was a disgustingly long episode to make for me. I'm sure it's going to take me like a week to edit, and I'm sure I'll get somebody complaining to me about how much my editing sucks, but that's the way it is. It's probably one of my least favourite things to do is making these videos. But I do know it's quite helpful to a few folks out there. I'm not sure when the next video will be, but I do hope you join me then. So I'll catch you next time.